For centuries, scientists believed plants lived in a silent world, communicating only through slow, drifting chemicals. But in 2023, researchers uncovered something far stranger. When stressed, tomato and tobacco plants unleashed bursts of ultrasonic clicks, 30 to 50 per hour, at frequencies our ears can never hear. It took AI to decode what these signals meant, and what emerged was a precise language of distress that shattered everything we thought we knew about the plant kingdom. The first messages translated didn't just surprise botanists, they unsettled them. If plants have been broadcasting urgent cries all around us, why have we remained deaf for millennia? The truth behind AI just decoded plant communication, and scientists are terrified of what they're saying, is about to rewrite the story of life itself. For decades, the scientific consensus held firm. Plants were silent, their communications limited to slow, invisible clouds of chemicals drifting through the air. Volatile organic compounds, VOCs, became the textbook explanation. When a caterpillar chewed a leaf, the plant would release a faint, scented warning. Neighboring plants, if they picked up the signal at all, might take hours or even days to react. This was the accepted script. Plants as passive broadcasters, sending chemical hints into the wind with no guarantee of being heard. The idea of real-time, rapid-fire communication was dismissed as fantasy. Even as researchers mapped the intricate web of underground fungal networks linking forests, they focused on the exchange of nutrients and chemical cues, not the possibility of instant messaging. The concept of plants actively signaling to one another, let alone doing so in a language outside human perception, simply didn't fit the models. Every major breakthrough in plant science, from the discovery of root exudates to the mapping of mycorrhizal connections, reinforced the view that if plants spoke at all, they did so in whispers, not shouts. This deep-rooted assumption shaped decades of research, leaving a blind spot for anything faster, sharper, or stranger. What was missing was a way to listen for signals that didn't ride on the wind, but cut through the air in a hidden register, signals that might overturn everything the textbooks had claimed. The first real evidence arrived in a basement lab at Tel Aviv University. Researchers placed tomato and tobacco plants inside soundproof chambers lined with acoustic foam, isolating them from every outside vibration. 10 centimeters from each stem, they set up specialized ultrasonic microphones, devices sensitive enough to pick up frequencies far above the range of human hearing. These microphones recorded at 500,000 samples per second, capturing every possible trace of sound between 40 and 80 kilohertz. For days, the plants sat in silence, monitored around the clock. But then the scientists introduced stress. Some plants went without water for 5 days. Their soil left bone dry. Others had their stems carefully snipped, a clean cut delivered with surgical precision. That's when the silence broke. Stressed plants began to emit rapid-fire bursts of ultrasonic clicks, sharp, discrete pulses, 30 to 50 per hour. The control group, those left untouched and well-watered, remained completely quiet. These clicks weren't background noise or mechanical artifact. Each one registered as a distinct acoustic event, invisible to human ears, but unmistakable in the digital traces. The drought-stressed tomatoes produced a different pattern than the freshly cut tobacco, as if each plant was broadcasting its own signature distress call. The numbers were impossible to ignore. 30, 40, sometimes 50 clicks in a single hour from a single plant under duress. For the first time, the idea of a silent plant world began to unravel, not with theory, but with hard, measurable data. What the researchers needed next was a way to make sense of these patterns, to decode what the plants were actually saying. To make sense of these sudden bursts of ultrasonic clicks, researchers turned to artificial intelligence. At MIT, a team of computational biologists built a machine learning model designed to listen for patterns hidden in the noise. The raw recordings from the Tel Aviv lab, hundreds of hours of plant clicks, became training data for the algorithm. Each audio file was broken down into thousands of features: frequency, duration, spacing, and energy of every click. The AI sorted through this information, separating the signals of drought-stressed tomatoes from the distress calls of freshly cut tobacco. With each iteration, the model improved, learning to spot subtle differences that no human ear could detect. In blind validation tests, the system reached an accuracy rate of 84%, high enough to distinguish a thirsty tomato from a wounded tobacco plant, even when background noise was added. This was not random static. The algorithm showed that each type of stress produced its own acoustic fingerprint, a signature embedded in the click patterns. The findings left little doubt. The plants were not just making noise, but broadcasting specific information about their condition. For the first time, the language of plant distress had been decoded not by intuition or guesswork, but by hard computational evidence. The question was no longer whether plants could send messages, but who, if anyone, was listening. In a dense forest in British Columbia, researchers set up a new kind of experiment, one that would test whether plant distress calls could travel not just through air, but through the living web beneath the soil. The team chose a stand of young birch trees, all linked by a sprawling network of mycorrhizal fungi. These microscopic threads, thinner than a human hair, connect roots across entire forests, forming what some call the wood wide web. To test the network, scientists released aphids onto a single tree, while acoustic sensors and chemical monitors kept watch on its neighbors, some as far as 30 meters away. Within seconds, the attacked tree began emitting rapid, ultrasonic clicks, its own version of an alarm. But the real surprise came minutes later. Trees connected through the fungal network, but untouched by aphids, started to release defense chemicals, volatile organic compounds that ward off insects, before a single aphid had crossed the gap. The timing was impossible to ignore. Defense responses synchronized across the network, all triggered by a signal that moved faster than wind or water could carry. The AI's analysis of the ultrasonic data confirmed it. The alarm call had traveled through the fungal network, prompting a coordinated chemical defense. For the first time, an entire forest was caught in the act of collective self-defense, acting as a single, responsive organism. This was not the slow, uncertain world described in textbooks. It was a living network, alert and ready to respond to threats in real time. Competition in the plant world is anything but gentle. Black walnut trees, for example, saturate the soil with juglone, a chemical weapon that cripples the roots of nearby maples. But the story doesn't end with toxins. When researchers placed ultrasonic sensors in walnut groves, the AI detected a barrage of low rhythmic clicks, an acoustic signature that spiked whenever juglone levels rose in the earth. These weren't random pops. They resembled the steady beat of war drums, pulsing through the underground network. Maples caught in the crossfire showed stunted growth or even chemical countermeasures of their own. In the Amazon, scientists have traced similar patterns, trees leveraging their fungal partners to sabotage invaders at the forest edge. What looks like peaceful green is, in reality, a battlefield, where alliances shift and rivals are suppressed by any means available. The implications of decoded plant communication stretch far beyond the forest floor. When NASA satellites tracked global vegetation health, they noticed synchronized waves of distress signals, entire continents of crops shifting from green to brown in lockstep during heat waves. Machine learning flagged these patterns as more than coincidence, hinting at a planetary-scale feedback loop. In high-tech labs, scientists ran a different kind of test. A so-called nurturer and assaulter would approach plants in controlled chambers. The plants reacted, sometimes emitting stress clicks before a hand was even raised, raising uncomfortable questions about recognition and memory without a brain. Meanwhile, patent offices quietly filled with applications for bioacoustic surveillance, systems that could eavesdrop on fields or forests, listening for distress calls, or even coordinated resistance. At the Max Planck Institute, researchers tracked the explosive spread of herbicide resistance among superweeds, tracing gene transfer through fungal networks that spanned continents. Some botanists now wonder if allergy epidemics are a form of counterattack, with pollen output spiking after urban vegetation detects chemical threats. The silent world of plants, once thought passive, now looks more like a restless intelligence, one that humanity may have underestimated for far too long. In 2023, researchers recorded tomato and tobacco plants emitting 30 to 50 ultrasonic clicks per hour when stressed, signals invisible to human senses for millennia. Machine learning models then achieved 84% accuracy in decoding these sounds, distinguishing drought from damage. For decades, science viewed plant interactions as slow chemical exchanges, but experiments with mycorrhizal networks revealed real-time alarm signals passing between trees, triggering defenses before threats arrived. The documented chemical warfare of black walnuts, paired with detectable acoustic patterns, overturned the image of tranquil forests. Yet the full extent of this language remains unknown. Scientists have not mapped every signal or its meaning. While evidence confirms plants can warn allies and suppress rivals, whether these abilities translate beyond current findings is unresolved. Today, forests are seen as dynamic networks, not silent backdrops. The evidence forces a new understanding. Plants communicate, compete, and coordinate in ways only recently revealed by technology. What else they are saying and how much we have missed remains an open question.